Okay, now we want to see a couple of more things about the triangles. So I'll state a theorem which follows by calculation. So we have a triangle alpha beta. What is its area? Well, here's a remarkable fact. The area of triangle is pi minus alpha plus beta plus gamma. Well, I mean, their existing a formula is not very remarkable. What is remarkable about this is for all triangles, okay, the area of whatever triangle is less than or equal to, strictly less than, less than or equal to pi. This is very remarkable because when you can't, in Euclidean space, of course, you can make a triangle as big as you like. So this is saying that you have something absurd, namely that all triangles have area at most pi. Well, pi in fact turns out to be area of ideal triangle. Okay, fine. So now what we have seen is area ideal triangle is unique. So I'll just make a remark here. Easy to see that area of delta is less than or equal to area of ideal triangle. Okay, and we had already seen that there's a unique ideal triangle. So this is a well-defined quantity. So this is a unique. There's a single number which is this. But you would expect that number to be infinity. Okay, so I will just justify. I won't make this calculation. Why area of ideal triangle less than infinity? This is what we'll try to see in a picture. Let's turn to our upper half plane and let's take a triangle. It has one side here, a second side here, and a third side here. Well, I can take a sort of barycenter. This point in this upper half plane, it doesn't look much like that. Okay, let's draw it here. The triangle is symmetric, so that we have seen. So there's a point which is equidistant from three sides. So all you need to show is that the area here is finite. Okay, this area finite. Okay, but to show that, we'll instead cut off here. Okay, and then show that this area is finite. Well, what is this area? Okay, so we want to show this area. Let me just clarify here. This point here is I, okay, which is 1 times I. I'll write it as 1 times I. So this is actually, that is the y coordinate is 1, and this goes off to infinity. So this point has to be just 1, and this point has to be minus 1. Okay, so what is this area? This is the integral where x goes from minus 1 to 1 and y goes from 1 to infinity. Okay, I could have put them in the other direction, perhaps I will. So let's turn this around instead. Y goes from 1 to infinity, and then x goes from minus 1 to 1. Okay, of what is our scaling factor? It's 1 over y squared. Okay, that's because hyperbolic matrix scales by 1 over y, so area scales by square of the length times dx dy. Dx is the inner limit. Okay, this is of course integral of 2 by y squared dy from 1 to infinity, which is 2. Well, 2 happens to be less than infinity. Well, of course, this is only the area of one piece. Okay, so this is an upper bound for about for the area of this part. Okay, I got slightly worried because 2 is not bigger than pi, but of course we have 3 such cusps. So what we get from this calculation is that hyperbolic area is less than 6, and of course 6 is an upper bound for pi, which is the true value. So what I was illustrating is that when we want to see that the area is finite, and this is the qualitative property that's extremely important. So let's conclude something from this. This will be our final conclusion about triangles. in this segment, and which will let us transition to geometric group theory, which is thin triangles. You see, what we have is we have ideal triangles. They have infinite diameter. We saw geodesics have infinite length, so they have infinite diameter. Or if we take a real triangle, they have as large a diameter as you want. So large diameter, and we have small area, or rather, let's be accurate, bounded area. The area need not be small, but it's bounded area. Well, how is this even possible? Well, it's possible if thin. The only way you can have something, well, so let me draw a picture of something with a very large diameter but very small area. Well, it has to be very thin. Actually, it can have a little bulge here. So thin for most of the whatever object we are talking about. So having a large diameter but bounded area means that you're mostly very thin. You can have a little fat part which captures some of the area. Okay, so here's the thin triangle theorem. Okay, so there exists delta greater than 0, and this is, let me emphasize, universal. It doesn't depend on anything. It just depends on hyperbolic space, nothing at all. It's a universal constant as far as hyperbolic space is concerned. There exists delta greater than 0 such that if L1, L2, L3 are sides of a triangle, then L1 is contained in the delta neighborhood of L2 union L3. Okay, so what this is saying is that I have L1, I have L2, and I have L3. This is how a typical triangle looks. Given any point here, a point here is close to, so let me call this side L1. A point here is close to L1. A point here is close to L2. A point here is close to actually both of them. But any point is a distance at most delta from one of the other sides. Again, it's absurd in a Euclidean case. I mean, in a Euclidean triangle, if the triangle is big, the midpoint here is actually quite far from both these sides. Okay, it could be arbitrarily far by just scaling up. So this says that any side is close to it. Okay, so a sketch of the proof, a little hyperbolic geometry fact concerning areas I'm not going to prove now, but we'll return to areas when we look at geometric group theory. So let delta greater than 0, what is this constant, be such that the semicircle of radius delta has area greater than pi. Okay, so what this, so again the semicircle is correct. That is to say, there is a unique, so take a geodesic, take a point on it, and you look at this region. Okay, so this, suppose this is delta. What you require, suppose this is delta, what you require is the area of the semicircle is greater than pi. In fact, hyperbolic areas are greater than the corresponding Euclidean areas. So if pi delta squared by 2 is greater than pi, it's enough. Okay, so in fact we have something quite explicit, which is delta is greater than 1. By the way, pi is replaced by some other element. You can take a larger thing. So this depends only on the qualitative fact of area being bounded. So what is the argument? So a semicircle about some point P in L1 must intersect L2 or L3. Okay, so let me take a final picture to show you this. We'll look at a Euclidean picture where this is false. So in a Euclidean picture here, let's take a point P here, and let's take a semicircle of radius delta. Okay, and this doesn't intersect either of the other sides. Okay, so these are of course the sides L1, L2, L3. So what we know is area of triangle is greater than area of semicircle, which is greater than pi. So okay, inequality is okay. So what happens, what do we see from this? On the other hand, in the hyperbolic case, this cannot happen, and the only way in which you can rule this out is because if I take any point P and I take a semicircle of radius delta, it has to go and hit this side. Okay, so this concludes, so from this we conclude that any point on a side is close to one side or the other. So I'll leave you with the last picture. So this thin triangle sort of looks like a triangle on a tree, and that is the picture to keep in mind. Okay, so it's, you think of a tree, which is this simple tree here, and there a triangle is just a rather degenerate object which goes up like this and comes like this and comes like this. Okay, well, a hyperbolic triangle is not that degenerate, but this is the rough model. This is thin, this is very, very thin.